Hi folks, today we're going to consider the concept of multiplying vectors and trying to see what that means. So let's see how we might define the product of two vectors. So let's start with some geometric vectors. So say u is 30 east 10 degrees south and v is 40 west 20 degrees south. So I've got these two geometric vectors, and what would it mean to multiply them? So the first idea might be to just multiply the magnitudes. Okay. First question is, what does that really give us? And the bigger issue here is, what do we do with the directions? Nothing really seems obvious at this point, so let's consider maybe a couple of algebraic vectors. So let's say I've got the vector 2, 3, and here the vector 3, 5. And when we think about how we add and subtract vectors, we just add or subtract the individual components. So it could be that multiplying two vectors is just about multiplying the individual components. So here's 6 and 15. Again, it's not really clear what this would give us, certainly in any kind of physical way, but this might turn out to be useful. What we're going to use as our motivation to come up with a definition for multiplying vectors is, as we've been doing right from the beginning, is to go back to a physics problem. And I want you to consider the physics problem of, say, a kid in a sled, okay, that's being pulled by someone, okay? And I want you to consider the concept of work. So you know that work is given by the force in the direction of motion times the distance. Now here, this is a 2D problem because the direction of motion is here, whereas the force is being applied upwards. Okay, so we have a displacement vector, okay, and we have a force vector up here. But since we're only interested in the force in the direction of motion, we're going to be considering the x component of the force. And so work would just be defined as the magnitude of the x component of force times the magnitude of the displacement vector. Okay, so work is force times distance. Now, how do we find the x component? Well, we remember that finding the x component of vector is just about taking the magnitude of the vector and multiplying that by the cosine of the angle between the two vectors. Okay? So this is where the idea of what we call the dot product came about, is can we define an operation on two vectors that will produce a product of the components in the same direction. Okay, so the way in which we define what we call the dot product is you take the magnitude of the first times the magnitude of the second, and you multiply it by the cosine of the angle between them. So let's take a look at what properties this dot product would have. So first of all, you realize that you're multiplying, and I always think of multiplying as being in quotations, multiplying two vectors, yet the resultant, when you look at this here, is actually a scalar quantity, since each of the three expressions are all scalars. Okay. The other thing that hopefully you notice is, since these are all multiplications of numbers, doesn't matter if I take the magnitude of v times magnitude of u, we would get the same result. So this way of multiplying vectors is actually commutative. And one last thing that's very nice is if we bring this down to one-dimensional vectors, in other words, vectors along the real line, you realize that this definition for multiplying any two vectors in 2 or 3 dimensions collapses to just regular multiplication. Okay, because here if I've got 2 times 3, okay, which we can represent as the vector 2 times the vector 3, and we use this definition, well, magnitudes, 2 times 3 is 6, and since the angle between them is 0, this is equal to 1, that this definition for multiplying vectors just collapses to a regular multiplication in one dimension. Now, if one of them is actually negative, okay, so I've got the vector 2 times the vector negative 3. Well, the magnitudes, 2 times 3 is 6, and because the angle between them is now 180 degrees, and cos of 180 is -1, this produces -6. Okay, so that's something very nice about this definition of the product of vectors, because in one dimension it just becomes regular multiplication. Okay, now we know, or we've seen up until now, that while there's a lot of nice things about geometric vectors, algebraic ones are even nicer. So we need to find a way to define this product using algebraic vectors. Now, if we're lucky, it will turn out to be exactly what we hypothesized up here. Will it just be about multiplying the individual components? Okay, so this is where we now need to do some algebra to figure this out. Okay, so if we take two algebraic vectors, and I'll call the first one x1, y1, so I want to do this as generally as possible. V will be x2, y2. Okay, and we want to define u times v, or u dot v is really what we say. Okay, we know that we need that to be the magnitude of u times the magnitude of v times cosine of theta. Okay, but we now want to translate this to working with our algebraic vectors. In other words, we'd like to find a formula that involves only the individual components of the two vectors. So let's write this out. We have the magnitude of u is just x1 squared plus y1 squared. The magnitude of v is just x2 squared plus y2 squared. And then cosine of the angle between them. So this is where we have to start doing a bit of work, because we need to now write the cosine of theta in terms of the components. So we'll do this here separately. And what I'm going to use is a little diagram to help me out. So if I've got my two vectors placed tail to tail, okay, and I have the angle between them, and I realize that I can form a triangle. Okay, let's take this vector here, which would just be, since I'm going from v to u, this would be the vector u minus v. Okay, so like I said, trigonometry seems to be a good way to go. So I don't actually want to work with the vectors themselves. I want to work with the magnitudes of the vectors themselves. Okay, so let's here we've got information about the three sides of the triangle, and we want information about that angle. So here we're going to use the cosine law. So let's recall the cosine law. It's just the side opposite to the angle squared equals the sum of the squares of the two other sides. Okay, minus 2 times magnitude of u, magnitude of v, cosine of theta. Okay, so let's isolate cosine of theta here. Okay, so I have the magnitude of u minus v all squared. So the magnitude, so first of all, we get this vector by subtracting the individual components, and since we're squaring it, we get rid of the square root. So I'm going to skip a couple of steps here and go right to writing this out. So it would be x1 minus x2 all squared plus y1 minus y2 all squared. So again, I'm subtracting the two vectors, taking the magnitude, and then squaring that. And this is what I would end up with. Okay, then we'll bring these other two to the other side. So we need to subtract the magnitude of u squared, which would just be x1 squared plus y1 squared. And I also have to subtract the magnitude of v squared, which would be x2 squared plus y2 squared. Okay, and then we'll divide that whole thing by -2 times magnitude of u times magnitude of v. Okay. So this is our expression for cosine of theta, and we've accomplished what we needed to do. We've written cosine theta in terms of the components of the two vectors. So now we're going to stick this back in to our expression. Okay, so what do we have? And I think you can already see some nice things are going to start happening. So we have x1 squared plus y1 squared times x2 squared plus y2 squared. And those are the magnitudes of u and v. And now we're going to multiply by this expression here. Okay. Now, in order to save myself a bit of time, I'm actually going to start expanding these out because I'm going to want to try to simplify as much as I can. So let's multiply x1 minus x2 by itself. So we have x1 squared minus 2x1 x2 plus x2 squared. Okay, then we've got plus y1 squared minus 2y1 y2 plus y2 squared. Okay, and then we are going to subtract these. So hopefully I don't run out of room. Minus x1 squared minus x2 squared. Y1 squared. And then minus x2 squared minus y2 squared. All over this denominator. Okay. And here, this is where we see some nice stuff that's going to happen. Okay, so we've got these magnitudes that cancel out, these magnitudes that cancel out, and we see that all the squared terms will cancel out in this numerator. Okay, y1 squared, there do we have here y1 squared, and then finally y2 squared and y2 squared, and this very ugly expression now simplifies quite nicely. So if I take a look in the numerator here, I see negative 2, negative 2. All these things cancel out, and what I'm left with is just x1, x2 plus y1, y2. Okay, and this gives us a definition for the dot product using algebraic vectors. Now, first thing we notice is it's not quite as nice as we anticipated. So first of all, when we think back to our original hypothesis, okay, it never really made sense that this would be how the dot product is defined, since the resultant is a vector and we were looking for a scalar quantity. Now you take a look at this, you think maybe it might have been the magnitude of this vector, and we see that it indeed is not the magnitude of this vector. However, this is a fairly simple expression. Okay, so this now gives us a definition for the dot product of two algebraic vectors. So you just multiply the two x components and you add them to the product of the two y components. Something that's fairly simple. Okay? Now, again, because the dot product gives us a scalar quantity, it's often called the scalar product. Okay, and we'll take a look at an example in a second that will show that these two definitions are in fact equivalent. Okay, so what we're going to do now is take a look at an example to see that these two definitions are indeed equivalent. So let's go back to our example of u being 2, 3 and v being 3, 5. So if we use now our algebraic definition, we get u dot v is just equal to, well, 2 times 3 plus 3 times 5. Look how easy that was. So 6 plus 15 is 21. Now let's see if we can generate the same answer using our other definition. Now, of course, the first thing we're going to have to do is we're going to have to figure out the magnitude of each of these, and we're going to have to figure out the angle between them. So let's just draw these on a Cartesian plane. So here we've got 2 and 3. So there's one vector, and then we've got the vector 3 and 5 up here. So got this other vector. Okay, so we need to find this angle between them. How are we going to do that? Well, we'll find the angle for 3, 5, find the angle for 2, 3, and then subtract them. So as you can see, this is already a very long process using the first definition for the dot product. So we certainly were, even though we had to do all that algebra, it'll be well worthwhile. So let's find that. So if we find the angle for v, So we know that's tan inverse of 5 over 3. And if you check that out, you'll find that that's more or less 59 degrees. And then find the angle for u. So tan inverse of 3 over 2. And that's about 56.3 degrees. Okay, so the angle between the two vectors is just the difference between these two. So that's about 2.7 degrees. Okay, now we also need the magnitude of u. So magnitude of u is a square root of 2 squared plus 3 squared. So 9 plus 4, so that's about the square root of 13. And you take the magnitude of v, which is 9 plus 25, so 34. So that's about the square root of 34. And if you use the original definition for u dot v, we have the square root of 13 times the square root of 34 times cosine of 2.7. And if you stick that into your calculator, you'll see you'll get 21.000. You have a few zeros before you actually get to a number. So given that we made some approximations here, we see that we get the same result whether we use our very simple algebraic definition of the dot product or using what we call the geometric definition of the dot product. Okay, so what I want you to do is I want you to think about some more properties of the dot product. We've already seen that it's commutative. Okay, are there any associative properties, any distributive properties that you can think of? And the big one I want you to think about is, can you use the dot product to tell you something about two vectors that have a very special relationship? Okay, and I want you to think about that cosine theta. How can you make use of that cosine theta to possibly tell you something about the relationship between the two vectors? Okay, so that's our discussion on dot product. And just to give you a little taste of what's coming up, we may actually consider another type of product, because here we have a product of two vectors that generates a scalar. We're going to take a look at what it might mean to define a product between two vectors that also produces a vector and how that can be useful for us. Okay, that's it for now.